This is SpaceTime, Series 26, Episode 113. Coming up on SpaceTime, NASA's Webb Space Telescope discovers 21 new brown dwarfs. Geologists ask the question, why there's so few minerals on Mars? And physicists are closing in on the elusive neutrino. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
As it searches the distant stars and galaxies of the ancient universe, NASA's James Webb Space Telescope is also discovering equally fascinating objects much closer to home. And this week, astronomers have announced the discovery of some 21 brown dwarfs by the observatory. Brown dwarfs are transstellar objects. They fit into a unique category between the largest known planets, these can have up to 13 times the mass of Jupiter, and the smallest stars, known as spectral type M red dwarf stars, which have around 80 Jovian masses. That's about 0.08 solar masses. Put simply, brown dwarfs are objects that don't have enough mass to create the sort of core pressures and temperatures which trigger the fusion of hydrogen into helium, the process that makes stars like our sun shine. Brown dwarfs were first theorized back in the 1960s, but the first unambiguous detections weren't made until the mid-1990s, which we reported on this program at the time. One of the things which make brown dwarfs so fascinating is that some begin their lives as red dwarf stars. But as they evolve, they burn through so much of their core hydrogen fuel supply that they actually drop below the fusion threshold, transforming them from a star to a brown dwarf. On the other hand, other brown dwarfs start out simply as massive planets, gas giants like Jupiter, the biggest planet in our solar system. In fact, when you think about it, even Jupiter generates more heat than what it gets from the Sun. In fact, were Jupiter more massive, it would have become a brown dwarf. So, selecting and categorizing brown dwarfs is vital for exploring stellar initial mass function, understanding binary stellar evolution, and for increasing our census of stars around which potentially habitable planets could be orbiting. The new Webb brown dwarf candidate discoveries have been reported on the pre-press physics website archive.org and are part of the JADES and SEERS extragalactic surveys. JADES is Webb's Advanced Deep Extragalactic Survey, while SEERS is the Cosmic Evolution Early Release Science Survey. Both focus on distant ancient galaxies, and the newly discovered brown dwarfs were hidden deep in the data. The study's lead author, Kevin Hainline from the Stuart Observatory, says most of the 21 newly discovered brown dwarfs are located in the Milky Way's thick disk or in its halo, between 360 and 13,700 light-years away. Now that's well beyond the local stellar neighbourhood where most previous brown dwarf discoveries have been made, because that's where they're easiest to see. Their discoveries will force the rewriting of some textbooks. See, finding some of the brown dwarfs in the galactic halo on the outskirts of the Milky Way galaxy is at odds with what shape we think our galaxy is. And their atmospheric spectra also fails to match current brown dwarf models. And that raises further questions about their formation and evolution. While extragalactic deep fields are designed to point outside the plane of the Milky Way galaxy in order to minimize stellar contamination, the use of Webb's deep observations to collect these sources has implications for the population of objects outside the thick disk, which may be among the most metal-poor and older stars at these temperatures in the galaxy. There is simply a host of unanswered questions surrounding these new brown dwarf discoveries. For that matter, surrounding brown dwarfs, period. I mean, do they form out of the gravitational collapse of molecular gas and dust clouds like stars do? Or do they form by clumping and accreting of matter together like planets do? Astrophysicists think that as a brown dwarf cools about 100 million to 500 million years after its formation, strange things start to happen in its atmosphere. They're suggesting it's possible that dusty clouds of quartz and other minerals could form there. But more studies needed, and that's where James Webb comes in. This is SpaceTime. Still to come, we ask the question why there's so few minerals found on Mars, and physicists are closing in on the elusive neutrino. All that and more still to come on SpaceTime. So far, nearly 6,000 different minerals are known to exist on planet Earth. But after more than 50 years of investigation, only 161 minerals have so far been recorded on the red planet Mars, a dramatically lower number for a planet that shares so much in common with the Earth. Of course, Mars is a lot smaller than the Earth. The planet has a diameter about half that of ours. And it's not just smaller, it's also less dense. Although the red planet has just 15% of Earth's volume, its mass is only 11% that of Earth's. Now, all this means that the pull of gravity on the surface of Mars is only 38% as strong as the pull of gravity on Earth's surface. Still, Earth and Mars are both rocky planets, and they both have similar kinds of iron-rich rocks on their surfaces. Mars is often called the red planet because of its red iron oxides or rust on its surface. And like Earth, Mars has mountains and canyons, but they're much bigger on the red planet thanks to its lower gravity. For example, the tallest Martian mountain, Olympus Mons, is 3 times taller than Mount Everest, the largest mountain on Earth. In fact, Olympus Mons is the tallest known mountain in the solar system. And the deepest Martian canyon, Valles Marineris, is 4 times deeper than the Grand Canyon in the United States. And that makes this Martian gully the deepest known canyon in the solar system. Mars also has a much thinner atmosphere now, with atmospheric volume less than 1% that of Earth's. The atmospheric composition is also significantly different, primarily carbon dioxide based, while Earth's is rich in nitrogen and oxygen. But none of these differences can explain the lack of Martian minerals compared to the Earth. Now, the difference, according to a new study reported in the Journal of Geophysical Research Planets, may have arisen because minerals on Mars have had fewer pathways to form compared with those on Earth, even though both planets began on very similar trajectories for mineral evolution. Following on research to catalogue mineral formation and evolution on Earth, scientists conducted a systematic study of all 161 known Martian minerals revealed through the past half-century of Martian missions and analysis of Martian meteorites. Whereas earlier work has identified some 57 primary and secondary mineral-forming mechanisms on Earth, this new study identified just 20 modes for mineral formation on Mars. It's fair to say that early in the planet's histories, minerals on Earth and on Mars probably formed in similar ways. For instance, the first minerals on both planets most likely crystallized directly from cooling magma. Hydrothermal activity would have also led to many new minerals on each planet. However, Earth's array of minerals went through extensive stages of diversification billions of years ago with the onset of plate tectonics and, of course, the proliferation of life, processes not known to have occurred on Mars. Although there are undoubtedly many more mineral phases on and below the Martian surface yet to be discovered, the researchers note that the total count of Martian minerals is still likely to be an order of magnitude smaller than that for Earth. And that remains a mystery. This is SpaceTime. Still to come, closing in on the elusive neutrino. And later in the science report, a new study has confirmed that AI chatbots are now every bit as good as your average human when it comes to creative thinking. All that and more still to come on SpaceTime. The humble neutrino is the most common form of matter in the universe, and they're so tiny that billions of them are passing effortlessly through you every second. Yet their importance to the makeup of our universe is simply unequalled. They're generated through radioactive decay in stars, in supernovae, in nuclear explosions, in particle accelerators, and in atomic reactors. Neutrinos are so named because they're electrically neutral, and because their rest mass is so small, it was long thought to be zero. Having almost no mass, neutrinos are capable of being accelerated to almost the speed of light. And as far as we know, they come in 3 flavors or types: the electron neutrino, the muon neutrino, and the tau neutrino. Each has its own specific properties. Now, confusingly, these 3 flavors of neutrinos don't line up specifically with 3 mass species. It seems each of the three flavours is made up of a quantum mixture of the three mass species. So, for example, a particular tau neutrino would contain bits of all three mass species. And those different mass species are important because they allow the neutrino to oscillate between the three flavours. So, an electron neutrino produced through, say, a beta decay reaction may interact in a distant detector as a muon neutrino or a tau neutrino. Now, although neutrinos don't have an electric charge, they do have their own corresponding antimatter counterparts, identified by the opposite chirality or handedness. Another important characteristic, which we alluded to earlier, is that neutrinos are very weakly interactive with other matter, reacting really only through gravity and the weak nuclear force. Again, that's why billions are passing right through you without you noticing them. Now, to fully explain how our universe came into being, we need to know the mass of the neutrino. And now a group of scientists called the Project 8 Collaboration have developed their own distinctive strategy to try and measure the neutrino mass. Once fully scaled up, Project 8 could help to reveal how neutrinos influence the early evolution of the universe as we know it. Now, back in 2022, after decades of research, a group of scientists known as the Catron team were able to set an upper limit for how heavy a neutrino could possibly be. Now, these results don't solve the problem. All they do is simply narrow down the search window, and the ultimate goal of determining a neutrino's real mass remains. Now, in a report in the journal Physical Review Letters, the Project 8 Collaboration are suggesting a new technique, one to reliably track and record a natural occurrence called beta decay. Now, every event emits a tiny amount of energy when a rare radioactive variant of hydrogen called tritium decays into three subatomic particles, a helium ion, an electron, and a neutrino. The ultimate success of Project 8 hinges on an ambitious plan. Rather than try to detect the neutrino, which effortlessly passes through most detector technology, the research team has instead decided to look at the total mass of the entire tritium atom, which equates to the energy of all its parts. They then measure the energy of a free electron generated by beta decay, and we know the total mass. So the missing energy must be that of the neutrino's mass and motion. One of Project 8's principal investigators, Brent van der Vende from the US Department of Energy's Pacific Northwest National Laboratory, says that in principle, with technology developments and scale-up, they have a realistic shot of getting into the range necessary to pin down the neutrino mass. Now, the neutrino is going to be incredibly light, over 500,000 times lighter than an electron. So when neutrinos and electrons are created in the same way, the neutrino mass has only a tiny effect on the electron's motion, and the authors want to see that small effect. So they need a super precise method to measure exactly how fast the electron's zipping around. To do this, Project 8 are relying on a technique called cyclotron radiation emission spectroscopy. It captures the microwave radiation emitted by newborn electrons as they spiral around a magnetic field. These electrons carry away most, but not all, of the energy released during a beta decay event. And it's that missing energy that can reveal the neutrino mass. This is the first time that tritium beta decays have been measured and an upper limit placed on the neutrino mass using the cyclotron radiation emission spectroscopy technique. Co-author Talia Weiss from Yale University has spent years with her Project 8 colleagues trying to figure out how to accurately tease out the electron signal from all the electronic background noise.
The neutrino is incredibly light. It's more than 500,000 times lighter than an electron. So when neutrinos and electrons are created at the same time, the neutrino mass has only a tiny effect on the electron's motion. We want to see that small effect. So we need a super precise method to measure how fast the electrons are zipping around.
The team's interested in tracking these electrons because their energy is key to revealing the neutrino mass. While this strategy has been used previously, the cyclotron radiation emission spectroscopy detector measures that crucial electron energy with the potential to scale up beyond the existing technology. And that scalability is what sets Project 8 apart. Co-author Elise Novitsky from the University of Washington says no one else is trying this technique because it's a kind of Wild West approach.
Nobody else is doing this, and so we're not taking an existing technique and, trying to tweak it a little bit. We're kind of in the Wild West. We do have engineers who are crucial to the effort. It's kind of out there from an engineer's point of view. Often experimental physics is kind of at the boundary of physics and engineering. You have to get particularly adventuresome engineers and practical-minded physicists to collaborate to make these things come into being, because this stuff is not in the textbooks.
In their most recent experiment, built at the University of Washington, the team tracked 3,770 tritium beta decay events over an 82-day trial window in a sample cell the size of a single pea. The sample cell is cryogenically cooled and placed in the magnetic field in order to trap emerging electrons long enough for the system's recording antennas to register a microwave signal. Importantly, the team measured no false signals or background events that could be confused for the real thing. Now that's important because even a very small background can obscure the signal of neutrino mass, making interpretation of useful signals more difficult. Co-author Noah Oblath from Pacific Northwest National Laboratory helped to develop the suite of specialized software needed to take the raw data and convert them to signals that can be analyzed.
Most experiments have, a 50 or 100-year history, at least, of the detection technique that they're using, whereas this is really brand new. Project 8 is not only a bigger and better CRESS experiment, it is the first CRESS experiment and was the very first thing to ever use this detection technique. It had never been done before.
Now that the team have shown their design and experimental system works using molecules of tritium, they have the next real barrier ahead. This will involve working on a system that produces, cools and traps individual atoms of tritium. And it's tricky because tritium, like its more abundant cousin hydrogen, prefers to form molecules. Now those molecules would make the ultimate goal of Project 8 unachievable. So, the team are developing a test bed to create and trap atomic tritium with intricate arrays of magnets that'll keep the tritium from touching the walls of the sample cell. Were they to do that, they would almost certainly revert to a molecular form. This technology advance will be the next step towards reaching and ultimately hopefully exceeding the sensitivity level achieved by the Catron team last year. For now, Project 8 are working on various designs for scaling up the experiment from a pea-sized sample chamber to 1,000 times larger. The idea there is to capture lots more beta decay events using a much bigger listening device, thereby going from the size of a pea to that of a beach ball. This report from the US Department of Energy's Pacific Northwest National Laboratory.
The universe is full of particles that we can't see or feel, and neutrinos are some of the most elusive of these subatomic particles. If we could learn more about the neutrinos' properties, we would be another step closer to understanding what happened in the first few moments after the Big Bang. An international team is leading an ambitious quest called Project 8 to measure the mass of the neutrino using a unique method of detection. The research team behind Project 8 is pursuing a strategy that involves cyclotron radiation emission spectroscopy, or CRESS. Here's how it works. First, the research team tracks and records a natural occurrence called beta decay. When a radioactive variant of hydrogen called tritium decays, 3 new subatomic particles are created: a helium ion, an electron, and the exotic neutrino. Neutrinos are extremely light compared to protons and electrons, so how will the team weigh them? That's where CRESS comes in. CRESS captures the microwave radiation emitted from newborn electrons as they spiral around a magnetic field. The electrons carry most, but not all, of the energy generated from this beta decay event. It's this missing energy the team is after. We can summarize with this simple equation. The total mass of a tritium atom equals the energy of its parts. When we measure the free electron and we know the total mass, the missing energy is the neutrino mass, bringing us one step closer to understanding the building blocks of the universe.
This is SpaceTime. time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study warns that AI chatbots are now every bit as good as your average human at creative thinking tasks. The findings, published in the journal Scientific Reports, follows a study which compared the ability of bots and humans to work out alternative uses for everyday objects. The test provides a good example of divergent thinking. So they pitted 153 humans against 3 AI chatbots on new uses for 4 objects: a rope, a box, a pencil, and a candle. They then graded their responses using 4 different categories: fluency, flexibility, originality, and elaboration. The researchers found that while the best human responses outperformed each of the chatbots' best responses in many categories, the bots were nevertheless able to perform every bit as good as the average human. And that's a significant advance. A new study has found that 2 months after Beijing's zero COVID-19 policy ended in December 2022, there was an estimated 1.87 million excess deaths in China. The findings, reported in the Journal of the American Medical Association, combined published obituary data from 3 universities in China with search engine data to estimate the excess deaths. The authorities say their estimated number of excess deaths far exceeds official Chinese government estimates of 60,000. Although the pattern of excess deaths was consistent with Chinese government reports that COVID-19 related hospitalizations and deaths had hit their peak at the end of December 2022. Excess deaths primarily occurred among older individuals and were observed in all provinces in China. Official figures now suggest some 7 million people have been killed by the COVID-19 coronavirus since it was first detected near China's Wuhan Institute of Virology around September 2019. However, the World Health Organization now estimates the true death toll is likely to be around 18 million, with some 770 million confirmed cases globally. North Korea has launched what it claims is its first tactical nuclear attack submarine. North Korean leader Kim Jong-un presided over the unveiling ceremony, saying the new nuclear-armed conventionally powered ballistic missile sub was part of a push towards the nuclear weaponization of Pyongyang's navy. Official images taken during this event revealed it's not really a new sub, but simply modifications made to an existing old Romeo-class conventionally powered submarine so that it could launch tactical nuclear weapons. The most significant modifications appeared to focus on accommodating more missiles. The missile section is now much longer, containing 4 launch tubes of about the same diameter as the 1,250-kilometre range Pukguksong-1 or the 1,900-kilometre range of the Pukguksong-3 missile, which could also accommodate the smaller diameter KN-23 short-range ballistic missile. There are also 6 launch tubes, most likely for the 2,000-kilometre range Hwasal-2 land attack cruise missile. But these larger tubes could not accommodate the North's newer, larger Pukguksong 4, 5 and probably 6 submarine-launched ballistic missiles. According to the US-based think tank Nuclear Threat Initiative, North Korea is estimated to have between 64 and 86 submarines. That theoretically gives it one of the world's largest fleets. However, most experts doubt that all of them are operational given their age. Apple have now released the new iPhone 15 range with advanced technology and eye-watering prices to match. With the details, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
Yeah, so the big change that has been long predicted was USB-C. So on the iPhone 15 and 15 Plus, that is at USB 2 speeds as far as I'm aware, but of course you've got the convenience of USB-C, the same connector that charges iPad Pros, Macs, and all the Android phones. So if you go to a friend's place, they have an Android phone, finally you can use the same charger if you've upgraded to an iPhone 15. Now, the iPhone 15 and the 15 Plus also now have the 48-megapixel camera that was in the iPhone 14 Pro from last year. And because of the larger sensor size and more pixels, they can actually give you a 2x image, 2 times optical zoom equivalent image without having that third optical zoom lens. So previously the zoom was digital. Now, because of the bigger sensor size, they can give you that larger 2 times image, which is really cool. And you also have the dynamic island, which is that little bubble of space at the top that can show you how far away your Uber ride is, or your meal is, or what the sports scores are, or if you're using a timer or a stopwatch, who's calling you, or how much charge is left on your AirPods, for example, without having to actually go into another app. Now, we also have the iPhone 15 Pro models, and the Pro Max, bigger one, actually has a 5 times zoom capability. Even though it's only got a 3 times telephoto lens, it's got this tetra prism inside that bends the light 4 times. Apple's not using a periscope zoom, they're using a different sort of zoom. Watch the keynote for the details on that. But it is the biggest zoom that we've had on an iPhone. There's actually the equivalent of 7 lenses inside, which is going to be really cool for people who are mad about photography. And so there's an 0.5 times ultra-wide macro lens, a 1 times main 24 millimeter lens, which can also do 28 millimeters to 35 millimeters at 1 times. There's the 2 times telephoto 48 millimeter lens, and this new 5 times telephoto 120 millimeter lens. Now, they made the bezel on the Maxes slightly smaller, but the big news is that it's got USB-C. But this is USB-C that can do 10 gigabits of speed. It's USB-C 3.2.
This follows the European edict, doesn't it?
It does, yeah. That's why the iPhone 15 and the 15 Plus and the Pro and the Pro Max have USB-C. USB-C can give you 10 gigabit speed. So that's 80 times faster than the USB 2.0 that Lightning normally transfers at. And so it also means you can use USB dongles that have HDMI ports or other ports.
How does that compare to the standard USB 3 that we're all familiar with, the blue one?
Well, the USB 3, normally that was 5 gigabits, and then USB 3.1 was meant to be, I think, 10 gigabits. And then there's a 20 gigabit version. And the Thunderbolt standard is 40 gigabits. So it's not as fast. There was rumors that this was going to be using Thunderbolt, but that's probably for next year's iPhone 16 Ultra, because this Ultra version that people said might have been coming this year that would have been even bigger than the Pro Max, it didn't arrive. But because you've now got USB-C 3.2 that can do this 10 gigabits, you can now record video to an external SSD. It doesn't matter how much capacity your iPhone 15 Pro Max has. You can, using a USB cable and a USB-C SSD, record straight to an external device. So it's really turning into a much more pro-level device. One of the other things in the iPhone 15 Pro Max is the grade 5 titanium frame, which is lighter than steel. And we're talking about almost 20 grams lighter for the Pro Max. So look, there's lots of other features. I've got all the details at techadvice.life. I have all the videos from Apple which go into detail explaining the different phones, the different models. And there's also the 1 hour and 25-minute keynote. I definitely recommend you watch that. Again,
it's also got information on the watch there too, hasn't it?
They've got the new S9 main processor. And this is the first time in about 3 or 4 years that they've launched a faster processor. The previous processor was so good, so much ahead of the competition, they didn't have to update it. But they've had to update it finally now, and you'll get smoother performance. You'll get the ability for Siri to understand what you're saying without sending it to the cloud. So any responses where you ask it to start an outside walk or do this or do that will be processed much faster. The S9 has a 2000 nits maximum outdoor brightness. So when you're outdoors in the sun, the screen is twice as bright as before. And the Ultra 2 has a 3000 nits screen. So it's even brighter still.
And of course, the big question all the listeners want to know is, what about the cost?
Well, they do seem to have kept the cost the same, at least at the entry-level models. Now, with the iPhone 15 Pro, the 128 gig model is $999 in the US and $1,849, nearly double, in Australia. The 256 gig model is US $10.99, but Australian $20.49. 512 gig is US $12.99, but Australian $23.99. And the 1 terabyte model for the iPhone 15 Pro is $14.99 US and $27.49 Australian. Now, for the Pro Max, the bigger one with 6.7 inch screen, there's no more 128 gig tier. They start at 256 gig. That's $11.99 in the US, but $21.99 in Australia because of our terrible exchange rate. 512 gig is US $13.99 and $25.49 in Australia. And the 1 terabyte is US $15.99. In Australia, it's up to $28.99. Now, that's $100 or $200 more expensive than last year.
Yeah.
And look, unless you're loaded with cash,
you're
going to
paying
get that.
$3,000 for an iPhone, aren't you?
Well, yes, it's definitely an expensive phone.
That's Alex Zaharov-Reutt from techadvice.life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.